We are in Unit 6, and this is the third section, so this is Notes 3. Today we are going to be integrating exponential functions e to the x and a to the x, where a can be any constant. So let's do a quick review of the derivatives of these functions. So if we have y is equal to e to the x, or f is equal to e to the x, whatever, and we're looking for the derivative of e to the x is just e to the x, right? So we did that, gosh, maybe in Unit 2, I forget, but probably in Unit 2 we took care of that. Okay, so the derivative is the same as the function. Not many, we can't say that about many functions. All right, let's take a look at some number to the x. So let's just say like 2 to the x, or 3 to the x, or 5 to the x, or pi to the x, some number to the x power. So what is the derivative of that function? Okay, back in Unit 2, or whenever it was that we covered the derivatives, we went through why this is true. We went through the formula for this. So now I'm just reminding yourself the result of the process that took. When we first saw this, we took the natural log of both sides, and then we took the derivative of that, and we got this answer. But this is the way I remember. Okay, what I see when I see 2 to the x, or 3 to the x, or 5 to the x, I think, okay, it's like e to the x, but not quite. But it's like e to the x, not quite. So I begin by thinking, okay, I know I'm going to have 2 to the x in my answer, because that's the like e to the x part. Okay? However, it's not an e, so we need to multiply by the natural log of whatever the base is, in this case 2. Now, that's how I remember it. So if y is equal to 5 to the x, then the derivative would be natural log of 5 times 5 to the x. All right? So again, if you forget why we got that, then go back and refresh yourself. It's back there. You'll see it under derivatives of exponential functions. Okay? But that was our derivatives. Okay? So today we're going to take a look at integrations. So antiderivatives. So let's take a look at the antiderivative of e to the x. So let's remember what this means. This means this is equal to a function. This is equal to some function such that when we take the derivative of that function, we get e to the x, right? So of course this is just going to be e to the x, because the derivative of e to the x is e to the x. And then, as always, we add our constant of integration. So the integral, or the antiderivative of e to the x dx is e to the x plus c. Okay? All right, let's take a look at the antiderivative of like 2 to the x. Okay? So again, kind of same process. We're looking for a function such that when we take the derivative of that function, we get 2 to the x, right? So what function do we need to take the derivative of to get 2 to the x? Here's a 2 to the x. If we divide 2 to the x by ln of 2, we should get our 2 to the x, right? So this would be 2 to the x over ln of 2. Or another way to write that is 1 over ln of 2 times 2 to the x. Either way is fine. Plus our constant of integration. I think of this 1 over ln of 2 as undoing the derivative's constant. You undo that derivative's constant. Okay? So in general, the antiderivative of any number to the x power will be 1 over ln of that base times a to the x plus c. If you prefer, of course, you can think of this as a to the x over ln of a plus c. Either one, they mean the exact same thing. Okay? So those are what we're dealing with today. So let's look at some examples. Okay? Example 1. Let's say that we have the antiderivative of e to the 1 minus 3x dx. Well, this looks like a little u substitution, doesn't it? So I'm going to go off to the side. I'm going to let u be the exponent. So du will be negative 3 dx. So in place of the dx, what will we put in? Well, negative 1/3 du, or du over negative 3, is equal to dx. So in place of the dx, we're putting negative 1/3 du. And in place of the exponent here, we're putting u. So our integral becomes e to the u times negative 1/3, which I take outside, du. And now this is just like e to the x dx. So this is just negative 1/3 e to the u plus c. And then go back to our x's. In place of the u, I'm going to put what u is equal to. And there's our answer. Okay? So a little u substitution with that one. Second example. Okay. E to the 1 over x squared all over x cubed dx. Looks complicated, doesn't it? Looks a little complicated. If I can't focus this just a little bit more, it's a little bit blurry. Okay. All right. Looks a little complicated, so we're going to choose a u substitution, because if you see an e in here, we know what we're dealing with. We're dealing with this sort of thing, right? So I really only know e to the u, or e to the x, right? So let's let u be the exponent. So let u be this exponent, 1 over x squared. All right? Let's see what happens. Du will be, okay, the derivative of 1 over x squared. You can think of that as x to the negative 2. So the derivative will be negative 2 x to the negative 3, right? And then again, multiply over your dx like we always do. So this du is negative 2 over x cubed dx. All right. Do you see the dx over x cubed? And do you see the dx over x cubed there? So I'm just going to leave that there, and all I need to do is divide over the negative 2. So negative 1/2 du will be dx divided by x cubed. So in place of this dx divided by x cubed, I can put negative 1/2 du. In place of the exponent, I'm putting u. So our integral becomes e to the u. In place of all that is negative 1/2 du. So the negative 1/2 I'm taking outside, and then I had du here. And what's left? That's just e to the u plus c, right? So this is negative 1/2 e to the u, where u is 1 over x squared plus c. Not too bad. Let's take a look at example 3. The integral of, or the antiderivative of, e to the 2x plus e to the x plus 1, all divided by e to the x. I don't know why that still looks a little blurry to me. I don't like that. Okay, that looks a little bit better. Okay, So when we see this, I see a fraction, and I actually see that this exponent is bigger than this exponent, so I'm thinking divide, but I would be doing that anyway. I actually would be doing that anyway because I see a single thing down here. So we're going to divide, and we're going to get to divide this short way by just putting each term in the numerator over that denominator, right? So we have e to the 2x divided by e to the x. What is that? The bases are the same, so you subtract the exponents, and 2x minus x is x. So e to the x. 2e to the x divided by e to the x is just 2. And then 1 divided by e to the x, I need to write that as e to the negative x. Okay? Antiderivative of e to the x is e to the x. Antiderivative of 2 is 2x. Antiderivative of e to the negative x. Think about that. If you needed to, you could go over and do a little u sub. Du would just be negative 1 dx, right? So this is going to be negative e to the u, so e to the negative x. And think about that. When we were taking the derivative of e to the negative x, what was that? That was negative e to the negative x, right? Right? Plus c. So real quick over here, I'm just going to do like a stream of examples. E to the 2x, integral of e to the 2x. We would do a u sub. Du would be 2 dx, right? Bring the dx over. 1/2 du would be dx. So I'm replacing dx with 1/2 du. I'm replacing 2x with u. So this is 1/2 e to the 2x du. I'm sorry, e to the u du. So that's just 1/2 e to the u plus c. So the integral, or the antiderivative of e to the 2x dx is 1/2 e to the 2x plus c. What would the antiderivative of e to the 3x be? It would be 1/3 e to the 3x plus c. What would the antiderivative of e to the pi x be? 1 over pi e to the pi x plus c. Right? So what's the pattern there? This is what I was talking about. If this is your u, then you need a number out here to undo that derivative. The derivative is 2, undo the 2 by multiplying by 1/2. The derivative is 3, multiply by 1/3 to get rid of that derivative of 3. The derivative is pi, multiply by 1 over pi. This works, you guys, if your derivative is a number. If your derivative is a number, do that. If it's not a number, then go through the entire u sub process, okay? And this, by the way, will work for anything, not just e to the x. It'll work for natural log or whatever. It'll work for all of them. You undo your derivative's number, okay? But don't try to undo an x. If we had an x squared here, you'd have to go through it the long way with the u sub, which isn't that long, but it's just slightly longer. Okay. Example 5, the antiderivative of 7 to the x dx. Okay, let's recall. In my mind, this is like e to the x. So I know I'm going to have a 7 to the x. And now, the derivative would have a multiply by ln 7, so I need to divide by ln 7. Does that make sense? Again, you're undoing that number of the derivative. Number 6. x times 9 to the 3x squared dx. Okay, this is one where that exponent is a little bit more complicated. So let's take our time and go off to the side and say u is equal to 3x squared, that exponent. So du is 6x, and then multiply the dx over. And now I see here the x dx, and I have this x dx. So all I need to do is move the 6 and then in place of the x dx, I'm putting 1/6 du. So this will be 1/6, so I'm going to move that 1/6 outside. And then we'll have 9 to the u du. So this is 1/6 times, okay, here's my thought process. The antiderivative of 9 to the u has a 9 to the u in it, but we need to undo that multiplying by ln 9 and make it divide by ln 9, just like that. As a multiple choice answer, this would look like 9 to the 3x squared divided by 6 ln 9. And that's probably the multiple choice answer. This would be a safe stop answer for sure. What else could they do with that? They could apply some log properties. Okay, ln of 9 is ln of 3 squared, so that's 2 ln of 3. So they could change this to 2 times 6 ln 3. They could do that. I don't know that they would do that, but they could. They sometimes like to play around with natural logs in their multiple choice answers. So know your log properties pretty well. Okay? Alright, I just have one more example for you. Number 7. Say we have the antiderivative of 1 over 5 to the 2x dx. Okay, well we have to write this as 5 to a power. So this would be 5 to the negative 2x. If we bring that 5 to the top, we change the exponent to a negative exponent, right? Okay. So if u is the exponent, then du will be negative 2 multiplied by the dx. So in place of the dx, what are we putting in place of the dx? Negative 1/2 du, right? Negative 1/2 du in place of the exponent u. So this is negative 1/2 antiderivative of 5 to the u du, which is negative 1/2. Okay, 5 to the u divided by ln 5 plus c. So 5 to the negative 2x divided by a negative 2 ln 5 plus c. Okay? And that's it. It doesn't get just too complicated. What else could they do to this answer? Well, they could bring that back to the denominator and make it negative 1 divided by 2 ln 5. I want you to be careful here, because if I just write 5 to the negative 2x, what does that look like? You need to be really careful with your use parentheses properly here, okay? You certainly can't leave it looking like that, because that looks like natural log of 55 to the negative 2x, right? So we certainly can't do that. Even if we did a dot like that, it still looks like natural log of 5 times 5 to the negative 2x. And it's not. That natural log of 5 is sitting alone. So put parentheses around that natural log 5. To be safe, you could put parentheses around everything down there, right? But use parentheses to communicate what your answer is. Okay, this was a short lesson, and that's all I've got for you on this. So see how you do on this your homework for this.